The Browning M2 50 caliber machine gun stood unequivocally as the most devastating infantry weapon deployed by the United States during the Second World War. When secured to a static tripod, a proficient marksman possessed the capability to penetrate engine blocks at distances up to 800 yards, tear through aircraft fuselages 1,000 yards away, and unleash a torrent of 450 rounds per minute with unnerving accuracy. However, affixing that identical formidable weapon onto the pedestal mount of a Willys MB Jeep, hurtling at 40 miles per hour along a deeply rutted Philippine supply route, transformed it instantly into a weighty 700-pound encumbrance, utterly incapable of striking even a large target from close range. The fundamental issue did not lie with the weapon itself. The M2 had distinguished itself with formidable performance across every theater of conflict, from the arid expanses of North Africa to the snow-laden forests of the Ardennes. The true impediment was the mounting apparatus, specifically the M31C pedestal, a 32-pound steel pillar directly welded into a socket on the Jeep's chassis behind the passenger seat. Ostensibly, this configuration was intended to provide American reconnaissance detachments with mobile offensive capabilities. In reality, it equipped them with a firearm that vibrated, clattered, and discharged its rounds in an unpredictable cone-shaped dispersion spanning approximately 15 degrees, the very instant the driver engaged the accelerator. Envision a gunner bracing himself precariously in the rear of a Jeep, hurtling along a treacherous jungle path in March 1945. The M31C pedestal offered no discernible absorption of vibrations. Every jarring pothole, every tremor from the engine, every minute steering correction executed by the driver was transmitted directly through that rigid steel post into the weapon's receiver. Furthermore, the Browning's reciprocating bolt, a substantial 17-pound steel block violently oscillating back and forth 13 times per second, generated its own distinct harmonic frequency. When this intrinsic mechanical violence was combined with the severe external shocks from the road, the result was a weapon system utterly incapable of maintaining a stable sight picture for longer than half a second. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. The official Army Technical Manual, specifically document 9 Wempine 2132, issued in February 1943, briefly acknowledged this significant operational constraint in precisely 3 sentences, inconspicuously located on page 127. It stated, "Accuracy degradation is expected during vehicular movement. Gunners should engage targets from stationary positions when possible. Pricing. Sustained fire, while mobile, is not recommended for precision engagement." This essentially translated to a grim reality. The mounted machine gun served merely as an intimidating ornament unless the Jeep was brought to a complete halt beforehand. This deficiency was far from a trivial inconvenience. By the early months of 1945, American forces operating in the Pacific were engaged in swift, mechanized patrols through Japanese-controlled territories, where pausing even for a moment often spelled certain death. Convoys urgently required mobile suppressive fire, the ability to rake tree lines, assault bunker apertures, and compel enemy personnel to seek cover while the column advanced through treacherous ambush zones. A weapon that necessitated a full vehicle stop prior to engagement was not merely ineffective, it was a tactically suicidal liability. Gunnery Sergeant William Mercer, assigned to the 1st Cavalry Division's reconnaissance platoon on Luzon, meticulously documented this profound frustration in his after-action report dated February 12, 1945. He wrote, Engaged enemy machine gun position at approximately 200 YD, while vehicle in motion. Expended 87 rounds, 0 observed hits. Vehicle halted. Engaged same target stationary. Neutralized position with 23 rounds. The figures were unequivocally damning. Nearly 4 times the amount of ammunition was squandered, and only by immobilizing the vehicle did the weapon achieve any measure of efficacy. The Marine Corps encountered identical operational challenges across campaigns in the Philippines and Okinawa. Their Jeep-mounted .50 caliber machine guns could certainly instill fear, generate a significant volume of noise, and compel enemy infantry to take cover. Yet they proved utterly incapable of delivering reliable, lethal force while in motion. In the brutal context of island-hopping warfare, where every single yard of advancement exacted a heavy toll in human lives, an inaccurate support weapon was not just a source of profound frustration, it was, in effect, a criminal negligence. Staff Sergeant Raymond Cupp was not an engineer by trade. He had never attended specialized ordnance schools, nor had he delved into the intricacies of mechanical design, nor had he perused a physics textbook beyond his secondary education. He was simply a young man from a farming community outside Terre Haute, Indiana, whose formative years had been spent mending tractor suspensions and ingeniously improvising plow hitches when his father lacked the financial means for proper replacements. This practical expertise in agricultural improvisation was remarkably about to resolve an engineering conundrum that had baffled professional Army Ordnance Corps specialists for a full 2 years. Cupp arrived in the Philippines with the 37th Infantry Division in January 1945, where he was assigned as a gunner on a reconnaissance jeep. Within his inaugural week of patrol duties north of Manila, he had expended a staggering 1,000 rounds of .50 caliber ammunition and, by his own candid admission, had failed to strike anything he had aimed at. This disheartening experience deeply troubled him. Back in Indiana, he could expertly navigate his father's Farmall tractor across a freshly plowed field and maintain a surveying rod steadfast in its makeshift rear mount. Why, he pondered, could the sophisticated military not keep a potent machine gun stable on a platform specifically engineered for weaponry? The crucial insight dawned upon him on February 23, 1945, as he observed a Sherman tank crew servicing their suspension system. The tank's bogie wheels, the road wheels directly in contact with the ground, were each supported by independent vertical volet suspensions, comprising robust coils designed to absorb impact and effectively dampen vibrations before they could reach the main hull. Cupp intently studied these springs for 20 minutes, then returned to his jeep and regarded the M31C pedestal with a newfound perspective. The pedestal, he realized, was inherently rigid, completely, unforgivingly rigid. It directly transferred every particle of kinetic energy from the road into the weapon. What if, he mused, it were not so? For the ensuing 4 days, Cupp dedicated himself to procuring the necessary materials through various unconventional means. He salvaged 2 substantial compression springs from a damaged 2.5-ton truck's seat assembly, each capable of supporting approximately 200 pounds of vertical load. He then requisitioned a 5-foot segment of half-inch steel pipe from a combat engineer unit, falsely asserting it was needed for tent pole repairs. In exchange for an hour of acetylene torch operation from a Navy CB welder, he bartered 2 cartons of Lucky Strikes cigarettes, and he acquired without official authorization a sheet of 1/4-inch steel plate from a supply depot's inventory of damaged goods. The resulting design was remarkably uncomplicated, yet profoundly effective. Cupp meticulously cut the steel pipe into 4 distinct sections and welded them vertically around the base of the M31C pedestal, thereby forming a sturdy square cage. The lower end of each pipe section was welded to a steel plate, which was then securely bolted to the Jeep's frame. The upper end of each pipe section was welded to a second steel plate, which in turn cradled the pedestal itself. Between these 2 plates, nestled within each pipe section, Cupp carefully installed one of the compression springs. Consequently, the pedestal now gracefully floated upon 4 spring-loaded columns, rather than resting in direct, unyielding contact with the vehicle's frame. The underlying physics of Cupp's invention were more akin to agricultural engineering than military science. He had, in essence, constructed a magnified shock absorber, employing the identical principle found in his tractor's spring-mounted seat to effectively isolate the operational component from the source of vibration. Road shock would cause the springs to compress, which would then expand back to their neutral position, thereby transforming sharp, jarring impacts into a smoother, more attenuated motion. While the M2's inherent recoil would persist, the newly spring-mounted platform would absorb a significant portion of that energy, preventing it from feeding back into the vehicle's frame and creating a destructive feedback loop. On March 1, 1945, Cupp conducted an initial test firing of his modified mount on a stationary Jeep. The weapon functioned flawlessly. The springs compressed slightly with each burst, then promptly rebounded. No structural failures were observed. That very afternoon, he successfully persuaded his squad leader, Sergeant First Class Jack Delaney, to permit a test fire while the Jeep was in motion. They drove a half-mile circuit through an abandoned sugarcane field at 30 beat Maumpar, during which Cupp discharged controlled bursts at a pre-marked tree. The resulting shot grouping, while not perfect, demonstrated a groundbreaking level of possibility. For the first time, a gunner could actually observe his tracers arcing progressively toward the target, instead of wildly spiraling into random, unguided trajectories. Delaney promptly halted the Jeep, dismounted, and walked to the designated tree where he counted 17 impacts concentrated within a 2-foot circle at a distance of 150 yards. He then turned back to Cupp, his face a mixture of profound astonishment and a hint of trepidation. "That thing's not regulation," he declared. "We're using it anyway." The efficacy of Cupp's modification, and conversely, the failure of the Army's standard mount, can be attributed to a scientific phenomenon known as resonant frequency amplification. Although no one within the 37th Infantry Division would have articulated it in such precise terms, this is precisely what transpired inside that Jeep whenever a gunner engaged the trigger while the vehicle was in motion. The Browning M2's bolt assembly, weighing 17 pounds, travels approximately 6 inches backward with each shot, cycling at a rate of roughly 450 rounds per minute during sustained fire. This equates to 7.5 cycles per second, or a frequency of 7.5 hertz. Simultaneously, a Willys MB Jeep traveling at 40 miles over the typical roadway conditions prevalent in the Philippines generated vertical frame oscillations ranging between 8 and 12 hertz, depending on the specific terrain, with the most severe resonance occurring around 9.5 hertz when encountering regularly spaced ruts or washboard surfaces. When 2 distinct vibration sources operate at comparable frequencies within a rigidly connected system, they do not neutralize each other. Instead, They mutually amplify one another. This is the very same principle that causes wine glasses to shatter when a soprano vocalist hits a specific resonant note. The Jeep's frame. Vibration and the gun's recoil vibration possessed frequencies sufficiently close to each other that they generated constructive interference, thereby exacerbating the total movement far beyond what either source would produce independently. An engineering study conducted at Aberdeen Proving Ground in November 1943, a full 9 months before Cup was even deployed overseas, had definitively identified this exact problem in its test report, which was marked for internal review only. The report explicitly recommended the implementation of a vibration isolation mount incorporating elastic dampening elements with a natural frequency below 4 Hz to avert harmonic coupling. Regrettably, this crucial report remained archived in a filing cabinet because implementing the recommended solution would have necessitated a complete retooling of production lines at 23 distinct ordnance manufacturing facilities. 23 distinct ordnance facilities. Cup says ingeniously crafted springs, despite their improvised nature, exhibited a natural vibrational frequency of approximately 3.2 Hz, a characteristic derived from their specific dimensions and the loads they were designed to bear. Remarkably, this figure aligned almost perfectly with the precise engineering specifications laid out by experts at Aberdeen. Yet Cup had not arrived at this crucial measurement through complex mathematical computations or advanced theoretical physics. Instead, his understanding stemmed from an innate, practical knowledge. He simply recognized that tractor seats required supple, shock-absorbing springs to navigate uneven agricultural terrain smoothly, and by direct extension, his gunner's platform demanded an identical solution to achieve stability and comfort in similarly jarring combat environments. The second formidable challenge confronting the standard weapon system was the critical issue of recoil management. The formidable M2 heavy machine gun unleashed a potent force, generating roughly 1,800 foot-pounds of recoil energy with every single shot fired. The conventional M31C pedestal mount, designed with an unforgiving rigidity, unfortunately transmitted a full 100% of this immense energy directly into the Jeep's structural frame. This energy, in turn, rebounded through the unyielding connection, creating a detrimental feedback loop. The consequences were severe. When a gunner unleashed a 5-round burst, the weapon was already violently oscillating by the third shot, still reverberating from the initial recoil that had bounced back through the vehicle's chassis. By the 5th shot, the gunner was contending with a chaotic interference pattern of 3 distinct recoil waves, rendering the sight picture utterly useless, akin to attempting to aim through a rapidly spinning paint mixer. Cup's innovative spring-mounted system proved remarkably effective in mitigating this violent kickback. Approximately 40% of that formidable recoil energy was efficiently absorbed through the dynamic compression and expansion of the springs themselves. This energy was then beneficially dissipated as thermal energy within the spring metal, rather than being detrimentally reflected back into the weapon. This specific phenomenon is technically known as hysteretic damping, a principle that underpins the exceptional effectiveness of modern car suspension springs in providing a smooth and controlled ride. The residual 60% of the recoil energy still imparted movement to the gun, certainly, but crucially, without the amplifying feedback loop, this motion became entirely manageable. the weapon would gracefully rock back slightly on its springs, swiftly settle into position, and be immediately prepared for the subsequent shot, rather than perpetually vibrating from the preceding one. We hope you are enjoying this deep dive into military innovation. Please stay with us and watch the end of the video for more fascinating insights. We would be incredibly grateful for your like and subscription. Also, feel free to share where you are from and what you think about this compelling topic in the comments below. Beyond the purely mechanical aspects, there existed a third, often overlooked factor: the profound human element. A gunner operating a weapon affixed to a rigid mount was compelled to physically resist every single vibration with strenuous muscular effort, an exertion that inherently introduced additional, unpredictable movements into the aiming process. Cupp's ingenious floating mount, conversely, demanded significantly less muscular correction, because its integrated springs adeptly managed the gross movements and shocks. This allowed the gunner to concentrate invaluable attention on making fine, precise aim adjustments, rather than engaging in a ceaseless physical struggle with the weapon. The profound impact of this ergonomic improvement was quantitatively validated decades later through rigorous tests conducted at the Army Research Laboratory, which conclusively demonstrated that spring-isolated weapons resulted in a remarkable 35% reduction in gunner-induced movement when compared to their rigidly mounted counterparts, simply because the operator was no longer constantly overcorrecting for the weapon's uncontrolled oscillations. The profound irony inherent in this situation was that the fundamental principle behind Cupp's design was not, in fact, an entirely novel invention. Historical records show that the French military had already experimented with spring-isolated machine gun mounts as early as 1918, and the Germans had incorporated rubber isolation bushings into some of their aircraft-mounted weaponry. However, the critical flaw was that institutional knowledge rarely transferred effectively across the chasm of intervening wars or between disparate branches of military service. Consequently, by 1945, the American Army had firmly convinced itself, through doctrine and practical experience, that rigid mounts were intrinsically more stable and therefore superior. Cupp, through his pragmatic innovation, decisively disproved this ingrained belief, demonstrating unequivocally that true stability and mere rigidity are not synonymous. His work profoundly illustrated that, at times, the most genuinely stable platform is precisely the one that is engineered to permit a controlled degree of movement. The inaugural combat evaluation of Cupp's ingeniously modified mount unfolded on March 8, 1945, during a critical reconnaissance sweep positioned east of San Fernando. Cupp's squad, holding the third position within a 5-jeep column, was methodically traversing a dense coconut plantation when, without warning, Japanese infantry forces unleashed a torrent of fire from a cunningly concealed position situated approximately 200 yards to their left flank. According to standard military doctrine, the appropriate response called for the entire convoy to immediately halt, dismount their vehicles, and then engage the enemy from a static position. However, the discerning column commander, First Lieutenant Anthony Brucia, made a distinctly different and audacious tactical decision. He issued explicit orders for the jeeps to maintain their current speed and simultaneously returned suppressive fire while continuing to advance directly through the perilous kill zone. Cupp's jeep stood as the sole vehicle within the entire column that was equipped with the innovative modified mount. The gunners in the other 4 jeeps, utilizing their standard M31C pedestals, unleashed sustained bursts of fire that, while powerful, primarily served to shred palm trees, kick up plumes of dirt, and ultimately achieved virtually nothing of tactical significance against the entrenched enemy. In stark contrast, Cup meticulously fired 3 controlled bursts, expending a total of 22 rounds, and with astonishing precision managed to place 8 of those rounds directly through the enemy position, frontal cover. The immediate and decisive outcome was that 2 Japanese soldiers were killed instantly, and the remaining enemy forces swiftly withdrew from their position before the convoy had even fully cleared the ambush zone. Crucially, this engagement resulted in 0 American casualties. Lieutenant Bruscia, recognizing the extraordinary performance, meticulously filed his after-action report that very evening. The particularly pertinent section of his official communication read with striking clarity, "Staff Sergeant Cupp's modified weapon mount demonstrated marked improvement in accuracy during mobile engagement. Request ordnance evaluation for possible wider implementation." This succinct yet powerful endorsement underscored the profound impact of the field modification. That compelling request was subsequently directed to Captain Leonard Hartman, the ordnance officer for the 37th Infantry Division, who, on March 11th, personally drove out to meticulously inspect Cupp's jeep. Hartman's reaction was both immediate and, regrettably, entirely predictable, given the rigid military bureaucracy. He promptly declared that the modification constituted a clear violation of 3 distinct sections of Army Regulation 758, which specifically governed unauthorized alterations to officially issued equipment. Consequently, he issued a direct order for the springs to be removed and the weapon mount to be immediately returned to its standard, approved configuration. However, Cupp's squad leader, the resolute Sergeant Delaney, met Hartman's directive with an unwavering resolve. He curtly instructed Hartman to simply file the requisite paperwork, and without further discussion, left the springs precisely where they were. This act, while seemingly defiant, was not merely insubordination in the traditional sense. Rather, it embodied the unspoken, yet deeply understood, compact that frequently existed between frontline soldiers who faced immediate life-and-death situations and the rear echelon officers, whose responsibilities often centered on regulations and logistics. Delaney understood implicitly that Hartman was free to generate any official reports he deemed necessary, but his own paramount duty was to ensure his men possessed whatever equipment would keep them alive in combat. Thus the springs remained firmly in place. Word of Cupp's remarkably effective modification spread far more rapidly and efficiently than any official communication channels ever could. By late March, a mere few weeks after its combat debut, 3 other reconnaissance units within the 37th Division had already independently constructed their own versions of Cupp's ingenious mount, fabricating them using whatever scavenged materials they could procure. The 1st Cavalry Division, operating approximately 30 miles to the north, acquired knowledge of this innovation through the informal soldier-to-soldier grapevine. Promptly, they dispatched a warrant officer to meticulously examine Cupp's jeep. This officer diligently took precise measurements, captured detailed photographs, and even collected a spring sample, which he transported back to his unit's motor pool. Within a mere 10 days, the 1st Cavalry Division had successfully equipped 6 of their own jeeps with strikingly similar modifications, a testament to the undeniable efficacy of the design. The first truly quantitative combat data, offering irrefutable proof of the modification as effectiveness, emerged from the 7th Infantry Division on Okinawa in April 1945. Major Douglas Sinclair, who commanded a mechanized reconnaissance company, had proactively authorized his gunners to construct cup-style mounts after learning about the innovation from a sergeant who had recently transferred into his unit. Major Sinclair was known for his meticulous record-keeping, having assiduously collected data on ammunition expenditure versus confirmed enemy kills since January, primarily to justify his ongoing requests for increased allocations of .50 caliber ammunition. The numbers he compiled following the introduction of the modified mounts were stark and undeniably compelling. Between April 12th and April 28th, Major Sinclair's company engaged a total of 23 distinct targets while their vehicles were actively in motion. The jeeps equipped with the standard unmodified mounts averaged a staggering 187 rounds expended for every single confirmed enemy casualty. In stark contrast, jeeps outfitted with Cup-S modified mounts averaged a dramatically reduced 44 rounds per casualty. This represented an astounding 76% improvement in ammunition efficiency, a metric that translated directly and profoundly into a vastly enhanced combat effectiveness on the battlefield. Sinclair's comprehensive report included something arguably even more valuable than raw statistics: the direct, unfiltered testimony from the gunners themselves. Corporal Edwin Marsh, one such operator, penned a particularly poignant observation: "Can actually see where rounds are going now. Can walk fire onto target instead of just hoping something connects. Makes you feel like you're doing your job instead of making noise." This powerful statement captured the profound psychological and operational shift brought about by the modification. That final line from Corporal Marsh resonated deeply, highlighting a crucial truth: combat effectiveness extends far beyond mere mechanical performance. It is inextricably linked to the intangible yet vital factor of confidence. Gunners operating the modified mounts consistently reported feeling significantly more capable and in control, which in turn fostered a greater sense of aggression and initiative in engagements, ultimately leading to superior overall effectiveness. By May 1945, Cupp's modified mounts had, through entirely informal and unofficial channels, proliferated to at least 17 separate units operating across the vast and challenging theaters of Luzon, Okinawa, and Mindanao. Soldiers were actively constructing copies based purely on verbal descriptions and rudimentary observations from fellow servicemen who had witnessed the original design. Despite this undeniable field success, the Army's official position remained steadfast. These modifications were unauthorized, non-standard, and potentially dangerous. Yet, in the crucible of actual combat, the results unequivocally demonstrated that Cup-S illegal mount was demonstrably preserving both precious lives and vital ammunition in roughly equal measure. The inevitable bureaucratic collision was, by this point, unavoidable. This confrontation manifested in the form of a priority telegram, a stark message that arrived at General Walter Kruger's 6th Army headquarters on May 19, 1945. The dispatch originated from the office of the Chief of Ordnance in Washington, D.C., and was routed through Manila. Its content was remarkably blunt and uncompromising for official correspondence. It stated unequivocally that multiple field units were reporting widespread unauthorized modifications to the M31C pedestal mount, and the Ordnance Department demanded that these modifications be ceased immediately, pending a full and comprehensive safety evaluation. The telegram cited a litany of concerns, including potential liability issues, fundamental questions regarding structural integrity, and the very real possibility of catastrophic failure during sustained periods of intense firing. It concluded with a stark directive to definitively identify the source of the modification and to confiscate all non-standard equipment without delay. This uncompromising directive placed General Kruger in an utterly impossible and unenviable position. His forces were, at this precise moment, 2 months deep into the brutal grinding campaign to systematically clear the remaining tenacious Japanese resistance from the Philippine Islands, a conflict that was consuming ammunition at rates that already severely strained his precarious supply lines. Simultaneously, his reconnaissance units, the very men engaged in the most perilous, ambush-prone patrol work and suffering the highest casualties, were unequivocally reporting that Kupp's modified mounts had, for the first time, rendered their weapons truly functional and effective. And now Washington was demanding that he strip these proven life-saving enhancements from his equipment and force his troops to revert to the use of gear that everyone in the theater of operations universally acknowledged as woefully inadequate. In response to this untenable situation, Kruger acted precisely as pragmatic commanders have consistently done throughout the annals of warfare. He stalled for time. On May 22nd, he dispatched a carefully worded reply, stating that a thorough field evaluation of the reported modifications was actively ongoing, and that, crucially, the removal of equipment during active combat operations presented an unacceptable operational risk. This calculated maneuver successfully bought him a temporary reprieve and precious time, but it did not by any stretch resolve the fundamental underlying conflict between battlefield necessity and rigid bureaucratic regulation. It is important to acknowledge that the Ordnance Department was not entirely incorrect in its insistence on the necessity of safety testing. Unauthorized field modifications, hastily implemented without rigorous engineering oversight, have indeed tragically resulted in the deaths of soldiers when improvised welds failed catastrophically, or makeshift parts shattered under the immense stresses of combat. The core question, therefore, was not about the validity of safety testing itself, but rather whether the stringent requirements for such testing should take absolute precedence over, or instead be weighed against, the compelling and undeniable data demonstrating enhanced combat effectiveness. The potential for enhanced combat effectiveness held the power to supersede existing equipment data. Colonel Thomas Hriss, serving as the 6th Army's principal ordnance officer, found himself ensnared in an intricate dilemma, balancing two seemingly irreconcilable mandates. On one hand, his professional obligation dictated stringent adherence to equipment safety protocols and the crucial maintenance of supply chain uniformity, both undeniably valid and essential concerns within military operations. Yet, he was also privy to Major Sinclair, a compelling report from Okinawa, which unequivocally demonstrated a remarkable 76% surge in ammunition efficiency attributable to the new modifications. Furthermore, his numerous conversations with frontline gunners provided first-hand, qualitative evidence, confirming the genuine superiority and operational advantages offered by the adapted weapon mounts. On May 28th, Colonel Hurrius put forth a pragmatic proposition designed to bridge this divide, initiate accelerated field testing, leveraging the Sixth Army's own substantial resources. This rigorous evaluation would meticulously document all findings, culminating in a comprehensive set of recommendations to be forwarded to Washington. Should these trials conclusively affirm the safety and operational efficacy of the modifications, a concerted effort would be mounted to secure their official integration. Conversely, if the tests revealed any inherent problems or deficiencies, the modifications would be rescinded, with the collected data providing irrefutable justification for the decision. This approach sought to resolve the conflict through empirical evidence and systematic validation. The proposed testing regimen commenced promptly on June 2nd and concluded on June 15th, meticulously executed at the 6th Army Ordnance Depot, situated just outside Manila. Engineers orchestrated a controlled experiment, outfitting 3 jeeps with the innovative Cup-style modifications and juxtaposing them against 3 other vehicles equipped with the conventional M31C pedestals. All 6 vehicles were then subjected to identical operational courses, during which a wealth of critical data was painstakingly recorded, encompassing precise accuracy metrics, structural stress measurements under various loads, and detailed analyses of any observed failure modes. The comprehensive course elements included firing while traversing smooth paved roads, engaging targets over challenging rough terrain, conducting prolonged, sustained fire sequences involving 200 continuous rounds, and subjecting the mounts to extreme duress tests, incorporating deliberate, frame-jolting obstacles. The ensuing results were unequivocally decisive, demonstrating a profound disparity in performance. The modified mounts consistently exhibited a remarkable 71% improvement in shot grouping density when operating at speeds exceeding 25 vice-minute, a figure strikingly consistent with Major Sinclair's earlier combat data. Subsequent structural analysis revealed an exemplary performance, with an absence of weld failures, spring fractures, or frame stress levels that surpassed acceptable operational thresholds. The sole reported instance of failure was unequivocally attributed to human error. A test gunner intentionally over-tightened the mount bolts, causing a base plate crack, rather than any inherent design flaw within the modification itself. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. Captain Robert Yamaguchi, the meticulous engineer overseeing the tests, concluded his official report with an uncharacteristically direct and unambiguous statement. The modified mount is superior to standard equipment in every measurable category. Recommend immediate theater-wide implementation. Promptly on June 18th, Hendricks forwarded Yamaguchi's compelling report to General Kruger, accompanied by a cover memorandum that strongly advocated for the formal authorization of the modification and simultaneously requested Washington's official approval for its widespread field production. Kruger, recognizing the undeniable merits, swiftly endorsed the recommendation and transmitted it up the hierarchical chain of command to General Douglas MacArthur's Southwest Pacific Command. A period of prolonged anticipation then ensued as the critical report slowly navigated the notoriously sluggish bureaucratic channels, moving at what could only be described as a geological pace. Meanwhile, undeterred by the official delays, soldiers on the ground continued their independent efforts to fabricate these superior mounts. By late June, the innovative modification had transcended its initial adoption by reconnaissance units, extending its reach to vital military police convoys, critical forward artillery observer teams, and even ingenious tank destroyer crews who cleverly adapted the underlying principle for their 50 caliber coaxial mounts. The proverbial genie was unequivocally out of the bottle. Regardless of Washington's eventual decision, whether to approve, deny, or outright ignore the innovation, the modified mounts had become firmly entrenched. Their operational superiority was undeniable, and crucially, the soldiers who relied on them knew they worked. The official response finally materialized on July 3, 1945, a full 6 weeks after Kruger's initial submission and 3 months subsequent to Kupp's pioneering effort in welding the very first prototype. The War Department, after considerable deliberation, authorized the provisional field adoption of the spring-isolated pedestal mounts. This authorization, however, was contingent upon a comprehensive formal design review and the subsequent development of precise manufacturing specifications. In essence, while military units were now permitted to employ these enhanced mounts, the implicit directive was clear: don't expect official supply chain support yet. This provisional authorization from the War Department inadvertently created a peculiar and challenging logistical predicament. While units were indeed granted permission to deploy the modified mounts, the Army explicitly withheld manufacturing support, declined to issue standardized installation directives, and notably, would not provide essential replacement components. Consequently, every single spring-isolated mount utilized throughout the vast expanse of the Pacific Theater necessitated local fabrication, relying entirely on the disparate materials and technical proficiency that individual military units could independently procure, improvise, and assemble. For the dedicated ordnance companies and resourceful motor pool sergeants across the Philippines and Okinawa, this monumental undertaking swiftly became the defining summer project of 1945. Amidst this landscape of localized improvisation, the 86th Ordnance Company stationed at Tacloban emerged as the primary catalyst for systematizing production. Their astute commander, Major Harold Wexler, recognized with foresight that while ad hoc battlefield improvisation sufficed for a handful of jeeps, it utterly lacked the scalability required for widespread theater-wide implementation. Commencing in mid-July, Wexler's dedicated team embarked on a meticulous process of reverse engineering Kupp's original design, painstakingly transforming it into something closely resembling a formal production specification. Their comprehensive efforts included the precise measurement of spring rates, exhaustive documentation of welding methodologies, the creation of detailed dimensional drawings, and the establishment of pragmatic material substitution guidelines to address instances where optimal components were simply unobtainable. By July 28th, their diligence culminated in the successful compilation and publication of a comprehensive 16-page mimeograph manual, aptly titled Provisional Modification Instructions, 31C Pedestal Mount Spring Isolated Configuration. The manual itself was a testament to ingenuity, ingeniously treating material scarcity not as an impediment, but as an integral aspect of its adaptive design philosophy. For instance, if standard truck seat springs were unavailable, the manual furnished a comprehensive list of 6 viable alternative spring sources. These diverse options included robust aircraft landing gear components, intricate 105mm howitzer recoil assemblies, and even readily available bed frame springs albeit with the prudent caveat of needing to be doubled for sufficient strength. Addressing the potential absence of specialized personnel in situations lacking a certified welder, the manual thoughtfully provided detailed brazing instructions, leveraging tools and equipment commonly found in any motor pool. Furthermore, the prescribed steel pipe sections could be flexibly replaced with alternative materials like angle iron, square tubing, or, in dire necessity, even hardwood. However, the manual prudently cautioned that wooden mounts would necessitate replacement every 6 weeks due to their susceptibility to stress fractures, emphasizing the pragmatic yet temporary nature of such substitutions. The distribution of this vital manual transpired through the same informal grassroots networks that had initially propagated the original modification. Motor pool sergeants meticulously duplicated the manual and readily shared it with adjacent units, fostering a rapid, organic spread of knowledge. Specific anecdotes underscore this collaborative spirit. A chaplain en route to Okinawa thoughtfully transported a dozen copies in his personal duffel bag, ensuring their distribution among ordnance companies upon his arrival. Another singular copy made its way to the 24th Infantry Division stationed in New Guinea, where an enterprising lieutenant ingeniously reproduced an additional 30 copies, subsequently circulating them throughout his regiment. By early August, various iterations of the manual were documented in no fewer than 40 distinct locations across the expansive Pacific theater, with localized production efforts commencing wherever individuals possessed access to welding equipment and salvaged metal. The actual manufacturing processes varied wildly in their sophistication across different units. The 51st Ordnance Company on Luzon, for example, established an impressive assembly line capable of fabricating 4 complete mounts daily through the systematic use of standardized jigs and a dedicated team of welders. Their output demonstrated exceptional consistency, with mounts achieving near interchangeability, a hallmark of efficient production. Conversely, the 127th Infantry Regiment on Mindanao relied on a single corporal whose welding skills were described as marginal. This individual meticulously constructed mounts one by one, adapting each to the specific materials and configurations he could manage with available resources. Despite this artisanal approach, his mounts were undeniably operationally effective. However, no 2 of his creations were identical, necessitating custom-fitted replacement parts for each unique installation. Quality control procedures were similarly improvised, reflecting the ad hoc nature of the entire process. Certain units implemented comprehensive test-fire evaluations to meticulously ascertain a mount's operational readiness, ensuring its reliability before deployment. Others, however, adopted a more pragmatic and perhaps optimistic approach, simply bolting them on and hoping for the best. Indeed, instances of failure did occur. Some springs fractured prematurely after merely 50 rounds, welds occasionally succumbed to operational stress, and base plates sometimes deformed upon encountering challenging terrain. Yet the overall failure rate was surprisingly low, a testament to the inherent simplicity of the design coupled with generous safety margins. A robust spring engineered to withstand 200 pounds effortlessly bore the burden of a 60-pound gun and effectively dampened its recoil. Similarly, welds designed for gun mounts were seldom subjected to stresses anywhere near their structural limits during routine operation, contributing to their unexpected durability. By August 15, 1945, the very day Japan announced its surrender, The meticulous records of the 86th Ordnance Company indicated that 847 modified mounts had been successfully integrated onto Jeeps throughout the Pacific Theater. This figure, however, only represented units that formally reported their activities to the 86th. The actual aggregate total was likely closer to 1/200. The modified mount had undergone a remarkable transformation, evolving from a solitary sergeant's ingenious improvisation into a pervasive, theater-wide equipment enhancement in less than half a year. This remarkable achievement occurred entirely outside conventional channels, devoid of any official procurement contracts, without a single cent of allocated funding, and critically lacking formal approval, until the modification had already become ubiquitous. The profound irony of this situation was certainly not lost on the soldiers engaged in this critical work. Corporal James Dietrich, a welder with the 542nd Ordnance, encapsulated this sentiment in an August letter to his brother, poignantly observing, "We're building gun mounts the Army won't pay for to fix a problem the Army says doesn't exist. And every gunner who gets one treats us like we invented fire. I've learned more about how the Army really works in 3 months than I did in 3 years of following regulations." That profound lesson regarding the true dynamics of military innovation would ultimately prove more durable and impactful than the physical mounts themselves. While the direct operational presence of the spring isolated mount diminished after the cessation of hostilities, making its precise lineage increasingly obscure, its underlying principle endured. The vast majority of these Jeep-mounted modifications were systematically removed during post-war equipment decommissioning, often disassembled for their scrap metal value, or unceremoniously left behind in motor pools throughout the Pacific as military units commenced their rotation homeward. The Army's official position consistently maintained that these adaptations were merely provisional field expedients, rather than being acknowledged as permanent, standardized equipment. However, the fundamental principle that weapons platforms necessitate effective vibration isolation to maintain accuracy during movement had been unequivocally proven in combat conditions that no peacetime test could possibly replicate. The initial formal recognition of this critical principle finally transpired in 1948, when the Army eventually promulgated Technical Bulletin TB D984, bearing the descriptive title, Vibration Isolation for Vehicle-Mounted Crew-Served Weapons. Tucked away within the document's appendices was a spring mount design that bore an uncanny resemblance, appearing conspicuously familiar to any individual who had served in the Pacific Theater. While the spring rates were now meticulously calculated by professional engineers, a stark contrast to the educated estimations of a sergeant, and the materials were designated as officially procured items rather than improvised, scavenged components, the fundamental architecture remained unmistakably Cupp's original concept. It featured 4 resilient, spring-loaded posts effectively isolating the weapon mount from detrimental vehicle frame vibration. Conspicuously absent from the bulletin, however, was any direct mention of Cupp by name, any explicit reference to the widespread wartime field modifications, or any acknowledgement that frontline soldiers had been actively deploying this precise solution for a full 3 years, while ordnance engineers were ostensibly developing it. The Korean conflict significantly broadened the application of this ingenious concept. The M38 Jeep, which succeeded the venerable Willys MB from the Second World War, was offered with an optional factory-installed, spring-isolated mount for a 50 caliber machine gun, officially known as the M66C. These production versions incorporated advanced coil springs encased within sealed tubes, further enhanced by rubber bushings designed for supplementary damping. This sophisticated arrangement represented a significant technological leap compared to the rudimentary truck seat springs employed by Cup. Yet it fulfilled precisely the same fundamental purpose. Official gunnery manuals issued in 1951 explicitly highlighted that the M66C mount facilitated accurate and effective suppressive fire, even while the vehicle was in motion, achieving speeds of up to 35 miles per hour. This remarkable operational capacity was precisely what Cup had ingeniously devised 6 years prior, a capability that the Army had, ironically, initially deemed unauthorized and unsupported. The crucible of the Vietnam War witnessed a significant and dynamic evolution of this essential concept through the widespread deployment of gun trucks. These formidable vehicles were essentially standard cargo haulers, specifically the robust 1.2-ton M35s and the heavier 5-ton M54s, which convoy security units meticulously fortified, with armor plating and outfitted with an array of multiple machine guns, all in the critical effort to safeguard vital supply routes. By 1968, the machine gun mounts on these modified trucks routinely integrated spring isolation as a standard engineering practice, although the specific designs exhibited considerable variation, reflecting the distinct ingenuity and resources of the individual units responsible for their fabrication. For instance, the gun trucks belonging to the 523rd Transportation Company ingeniously utilized repurposed automotive coil springs. In contrast, the 8th Transportation Group showed a preference for the robust performance of aircraft shock struts. Meanwhile, the 39th Transportation Battalion creatively constructed their mounts using resilient rubber torsion elements cleverly salvaged from helicopter landing gear components. Despite this diverse array of implementations, the fundamental underlying principle remained universally consistent. It was imperative to effectively isolate the weapon system from the inherent vibrations of the vehicle, or otherwise resign oneself to drastically compromised accuracy. What proves particularly fascinating is the persistent observation that formal military engineering disciplines consistently lagged behind, never quite assimilating or catching up with the practical innovations developed in the field. Indeed, throughout the decades of the 1970s and 1980s, the officially sanctioned Army mounts for vehicle-mounted weaponry largely retained their relatively rigid designs, offering only a minimal degree of vibration isolation. Concurrently, frontline soldiers persistently undertook their own modifications, incorporating springs, rubber bushings, and various improvised damping systems, driven by the undeniable fact that the official issued equipment continued to fall short in performance. The profound institutional knowledge originally demonstrated by Cup, the critical understanding that dynamic, moving platforms necessitate effectively isolated weapon mounts, was repeatedly rediscovered by successive generations of soldiers, each confronting the challenge of accurately engaging targets from vehicles in motion. Please stay with us and watch the end of the video. We will be grateful for your like and subscription. I'm watching from London, and this video topic about bottom-up innovation versus institutional inertia in the military is absolutely fascinating and so true to life. The definitive and unequivocal vindication of this long-held principle finally arrived with the introduction of the M153 Krause, Common Remotely Operated Weapon Station, a sophisticated system that began its deployment on Humvees starting in 2007. CROWS represents an advanced, computerized turret system, empowering gunners to precisely aim and engage targets from the relative safety and comfort inside the vehicle, utilizing high-resolution cameras and intuitive joystick controls. The intricate engineering underpinning CRAOS encompasses highly sophisticated gyroscopic stabilization, advanced digital fire control mechanisms, and indeed every cutting-edge technological advancement one would anticipate from military hardware engineered in the 21st century. Yet, subtly embedded within the system's comprehensive technical specifications lies the crucial mounting interface, a meticulously engineered spring-isolated platform, further enhanced with active damping capabilities, all specifically designed to prevent vehicular vibration from adversely affecting weapon accuracy. This fundamental principle, originally forged by Cup in a Philippine motor pool, is now realized with precision servo motors and sophisticated computerized stabilization, but remains in its core purpose fundamentally identical. Contemporary military engineers will readily assert that the stabilization technology integrated into CRAOS draws its lineage from advanced naval gun mounts and sophisticated aircraft turret systems, a claim that is, from a technical standpoint, entirely accurate. However, if one meticulously traces the specific historical lineage of vehicle-mounted weapon isolation within the U.S. Army, the foundational thread undeniably leads back to reconnaissance jeeps in 1945, and to a perceptive sergeant who intuitively grasped that truly stable platforms need not necessarily be rigidly fixed. Raymond Cup himself never garnered formal recognition for his ingenuity, nor did his name ever appear in an official technical manual, and it is highly probable that he never realized his improvised mount would significantly influence weapon system design for the subsequent 7 decades. Nevertheless, every gunner who has successfully engaged and hit a target from a moving vehicle since that pivotal year of 1945 implicitly owes a debt to his original insight, whether consciously aware of it or not. The narrative of Raymond Cup, far from being an isolated incident in the annals of military history, instead represents a recurring and discernible pattern. Consider, for instance, the bazooka, a revolutionary anti-tank weapon, which was conceived and developed by a captain who boldly disregarded the skepticism of the Ordnance Department, proceeding to construct a working prototype in his own garage. Similarly, effective body armor capable of actually stopping rifle rounds emerged not from stringent procurement specifications, but rather from ingenious field modifications undertaken by soldiers themselves to improve their often inadequate issued vests. Even the up-armored Humvees, which ultimately provided crucial protection to convoy crews in Iraq, originated as initially unauthorized modifications. These were painstakingly fabricated by motor pool sergeants who welded together scrap metal and ballistic glass salvaged from battle-damaged vehicles. In each of these illustrative instances, the vital solution sprang from the actions of soldiers who, driven by necessity, transgressed established regulations, operating under the implicit understanding that the imperative of survival inherently superseded the demands of compliance. This pervasive phenomenon consequently gives rise to a profound paradox situated at the very core of military innovation. Military forces, by their fundamental nature, are hierarchical institutions whose operations are predicated upon stringent standardization meticulous regulations, and rigorously authorized procedures, and for entirely valid reasons. When the monumental task involves coordinating hundreds of thousands of personnel across diverse continents, the operational necessity for standardized equipment, reliably predictable supply chains, and universally followed procedures becomes unequivocally paramount. However, this very standardization, while essential, simultaneously engenders a significant institutional inertia, an inherent resistance to change, even when such change is unequivocally and desperately required. The elaborate procurement system, which meticulously guarantees that every soldier receives an identical reliable service rifle, concurrently ensures that any endeavor to improve that same rifle necessitates navigating through years of exhaustive testing, protracted approval processes, and complex budgetary negotiations. Frontline soldiers, by contrast, operate under a fundamentally distinct set of operational constraints and imperatives. Their immediate concerns do not encompass the intricacies of supply chain logistics or the complexities of procurement regulations. Instead, their paramount concern revolves around the immediate functionality of their equipment, specifically whether it performs effectively right now, within the unique and often perilous conditions they confront on a daily basis. When that critical equipment proves deficient, for instance, when machine guns fail to accurately engage targets from moving jeeps, when issued body armor proves incapable of stopping the actual rounds being fired, or when vehicles lack adequate protection against the prevalent threats, soldiers invariably take it upon themselves to rectify the issue, employing whatever materials and skills they can ingeniously improvise. This intrinsic drive is a clear manifestation of survival instinct decisively overriding established institutional processes, a recurring phenomenon observed in every armed conflict throughout history. The most astute and forward-thinking military organizations consciously acknowledge this fundamental reality and proactively establish formal channels designed to effectively capture and integrate field innovations before these resourceful solutions proliferate too widely beyond official oversight. During World War I, for example, the British Army maintained dedicated trench workshops where tools and weapons ingeniously invented by soldiers could be thoroughly evaluated and, if proven useful, rapidly moved into production. Similarly, the German military, during World War II, actively encouraged unit-level modifications and employed liaison officers specifically tasked with meticulously documenting successful field expedients for potential broader adoption across their forces. While these systems were undoubtedly imperfect, they crucially recognized the undeniable reality that soldiers would inevitably innovate, whether officially authorized or not. Consequently, the institution wisely chose to harness and leverage that inherent creativity rather than futilely attempt to suppress it. In stark contrast, the American military establishment in 1945 possessed no comparable systematic framework, a deficiency that largely explains why Cup's innovative mount disseminated through informal networks for several months before headquarters even became aware of its existence. By the time any official evaluation commenced, hundreds of soldiers had already enthusiastically embraced the modification, driven solely by its burgeoning word-of-mouth reputation and the compelling direct observation of its tangible, positive results. In essence, the system operated in reverse. Widespread adoption fundamentally preceded any official approval, and that approval only materialized because the modification had already become too pervasive to effectively suppress or ignore. This serves as a clear illustration of innovation occurring despite the institutional framework, rather than being fostered or enabled by it. A more profound truth emerges from this narrative concerning the actual individuals who are instrumental in solving critical problems. Cupp himself was neither a formally trained engineer nor an ordnance specialist. He was certainly not an individual whom the institutional army would have officially assigned the task of enhancing weapon mounts. Instead, he was a young man from a farming background, whose practical understanding of springs and vibration was honed through the everyday experience of repairing tractors. The crucial insight that ultimately resolved the persistent problem originated from his agricultural experience, rather than from conventional military expertise. This pattern of cross-domain problem-solving occurs with remarkable consistency. Truly critical innovations frequently emanate from individuals who apply knowledge acquired from entirely unrelated fields, precisely because they are not confined by preconceived notions of how things are supposed to work within a specific domain. For instance, an expert specializing in vehicle-mounted weaponry might never consider drawing solutions from tractor suspensions, primarily because tractors are not weapon systems. However, an individual possessing knowledge of both tractors and weapons is uniquely positioned to forge connections and devise solutions that specialists operating within narrower confines might entirely overlook. Contemporary military organizations continue to grapple with this identical paradox in the present era. The procurement system, unfortunately, has become even more protracted and bureaucratized, with the average development timelines for novel equipment often extending to a staggering 15 or even 20 years from the initial articulation of a requirement to its eventual fielding. Concurrently, the conflicts in Iraq and Afghanistan gave rise to immediate and urgent operational requirements, such as enhanced IED protection, effective counter-drone systems, and encrypted communication capabilities that reliably functioned in complex urban environments, needs that simply could not endure a 2-decade wait for official solutions. The inevitable consequence was yet another extensive wave of unauthorized field modifications, subsequently followed by a frantic institutional effort to legitimize and mass-produce the very solutions that soldiers had already ingeniously constructed for themselves. The overarching lesson derived from these experiences is not that regulations are inherently flawed or that soldiers should habitually disregard established procedures. Indeed, unauthorized modifications carry inherent risks. They can be perilous, lead to severe supply chain complications, and potentially introduce critical failures that tragically result in loss of life. Rather, the crucial lesson is that an inherent disparity will perpetually exist between the capabilities of issued equipment and the dynamic needs of soldiers, and that creative individuals will consistently endeavor to bridge this gap, irrespective of official regulations. The pertinent question for military institutions, therefore, becomes whether they choose to actively suppress this innate creativity, strategically harness it, or merely elect to ignore its existence until its widespread adoption renders it impossible to overlook. The historical precedent of Cupp's mount unequivocally demonstrated that the latter option, pretending it isn't happening, is ultimately ineffective. Soldiers will invariably innovate, regardless of official authorization, And the most effective institutional strategy is to swiftly recognize genuinely beneficial ideas, making them official policy before they become so ubiquitous that their suppression is no longer feasible.